Nice to meet you all. Today I'm going to talk about democratizing 3D human digitization by making it affordable, efficient, and easy to use. And if you have any questions, just feel free to interrupt and ask me questions. So before we talk about the human digitization, let me briefly introduce myself. So I did my PhD in UNC Chapel Hill with Professor Henry Fields. Is this nice, honorable person here? And he's the father of the computer graphics like augmented reality and virtual reality. And I really enjoyed my time back in while doing PhD in UNC. And after that, I moved to Pittsburgh, Pennsylvania to do postdoc with my another amazing advisor, Fernando here. He's a very nice guy and full of interesting ideas. So if anybody is thinking about doing PhD or like doing postdoc with him, I definitely recommend him. And after 1 year, I moved to Stanford to do another 1 year of postdoc with Isan here. He's also an amazing and very kind advisor. I really enjoyed my time there. And after that, last fall, I joined Emory University as an assistant professor, and now I'm leading Emory Vision and Graphics Lab, where we are working on human digitization for diverse applications in education and healthcare. And also we are working on 3D and 4D reconstruction and generations. So now let's talk about the 3D human digitization. So let's first begin with watching this short clip of Mark Zuckerberg and Lex Fridman having a conversation. So they are having a conversation like this, but actually what you just saw wasn't a real conversation between Mark and Lex, but it was their digital avatars. So digital humans are computer-generated representations of people created using computer graphics and computer vision like 3D modeling, motion capture, and animation. And digital humans have many interesting applications, for example, like telepresence. So telepresence is the technology that makes you feel like you're physically present with someone in the same space, even when you are far apart. So the two people in this video are also far away from each other, but it looks like they are in the same space. And this can be enabled by telepresence technology. And the core technology behind this is the human digitization. And another interesting application is sports. So with human digitization, we can navigate our favorite sports game freely as if we are one of the players. And also digital humans are used in creating virtual reality concerts like this. So unless you pay for a very expensive tickets, it is really hard to watch your favorite artists performing from close distance. But with human digitization, you can watch your artists right in front of you. So while 3D human digitization holds immense potential to enhance lives, current technologies face key challenges that limit their affordability. First, they rely on expensive hardware setups such as multi-view camera systems, depth sensors, or high-end GPUs. And also, the process involves labor-intensive and highly specialized steps such as scanning, rigging, and animating. Lastly, these systems demand controlled environments such as specialized studio with multiple lines. And together, these limitations prevent 3D human digitization from being widely adopted. So to overcome these limitations, my research focused on democratizing 3D human digitization by making it affordable, efficient, and easy to use. And I tackled this challenge through three key objectives. First, by reconstructing from sparse observations, which means developing methods that work with minimal camera inputs. And second, by designing efficient representations. And this means that we are targeting to reduce both computational cost and processing time. And finally, by creating easy-to-interact representations, allowing non-experts to manipulate 3D models effortlessly. So by addressing these challenges, my research brings us closer to a future where anyone, regardless of research or expertise, can benefit from this technology. So in today's talk, I will first discuss efficiency, affordability, and finally the ease of interaction. So let's first start with efficiency, specifically in the context of the animation task. So the challenge here is to design efficient representation that enable fast, high-quality animation without relying on high-end GPUs. To understand the difficulty of this problem, let's first take a look at existing methods and their limitations. So when I was working on this project, there were two major branches in the research of animatable representation. The first one is the explicit mesh-based methods. You can think of this approach as reconstructing the template, 3D template model first, and then optimizing the corresponding texture map that corresponds to each different frame. You can, for example, optimize textures of clothing and their changing wrinkles per frame. However, they are heavily dependent on the quality of the template mesh itself. So if errors are already existent in the scanned template, that means that they are directly reflected to the final render results. So there were those explicit mesh-based methods at that time. And also another branch was this neural radiance fields-based method, which combines also the 3D proxy mesh with the neural radiance fields. So these methods achieve high-quality results, but they are pretty slow due to their expensive volume rendering algorithm. So existing methods force a trade-off between the speed and the rendering quality. So what we need here is an animated representation that can achieve both the high quality and fast rendering time. To achieve this, I developed a deformable light field approach that extends the traditional light fields approach. So here, given target skeletal motion and camera parameters, our system can efficiently generate high-quality overviews and pose of the subject. So let me first talk about the neural radiance fields. As I mentioned earlier, at that time, neural radiance fields was the dominant approach for the neural rendering. And neural radiance fields is a function that maps, give me one sec, maps the 3D location and the viewing direction. What I mean by viewing direction is where this ray is pointed to. And this neural radiance fields is a function that maps those two inputs to the corresponding color and density value. And in order to render just a single pixel using the neural radiance fields, what we need to do is we first sample lots of 3D points. We sample lots of 3D points denoted with those small circles here on this viewing direction, and then we evaluate each of them. What I mean by evaluating is asking the neural radiance fields, what is the corresponding color and density value at this location? So we do this process for every sampled 3D points on this ray. And then after obtaining all the color and density values, let's say there are n points sampled, then we will evaluate n times. And then we do the weighted sum of them to get the final pixel color C at this point. And to render the entire image, we should repeat this process for every pixels on that image that we have. And this means that the rendering speed of the neural radiance fields is extremely slow. And this motivated me to search for another efficient representation, which is light fields. So light fields is a function that maps an oriented camera ray to the corresponding radius. So here we can think of a camera ray as an oriented ray, and our light fields can directly map this oriented ray to the corresponding radius. And since it only requires a single evaluation per pixel, its render speed is very fast, and therefore in this work, we adopted light fields as our representation. So to use the light fields, we should first decide how to parameterize array. And the camera array can be thought of as an oriented line, and we know that a line can be uniquely decided by two intersecting points. And this idea is adopted in the most popular and commonly used representation in light fields, which is called the two-plane parameterization. And here, array is parameterized by its two intersections with the two planes in front of the 3D scene that we want to render. So here, we are assuming that we have the 3D objects that we want to render here. And then to parameterize these rays, we place two imaginary planes in front of the 3D scene, and then we parameterize our ray with the two intersection points with the two imaginary planes. So again, the light field can be formulated as a function that takes the ray parameterized by two intersection points u1 and u2 and outputs the corresponding radius c. So however, the traditional two-plane parameterization is limited only to the rendering of frontal parallel scenes, and also it is designed to render static scene, and thus it is not applicable in our setting where we want to create an animatable representation. Therefore, in this work, we focused on how to adapt the traditional two-plane parameterization to animatable light fields. So there are two desired properties of the animatable light field parameterization. So firstly, it should be able to parameterize a full 360-degree ray space, and second, it should be animatable. So I will first talk about how we can parameterize a full 360-degree ray space. So let's say that we are looking at the surface of the simplified human from the bird's eye view. So let's say this is our simplified human. And let's say that we want to parameterize this incident blue ray. So if we place two planes here, if we place two imaginary planes here, this ray can be represented with those two intersecting points, those yellow and green intersecting points. However, the other rays coming from different directions, such as those red colored rays here, cannot be represented. And this means that we cannot fully parameterize the 360-degree ray space with the two-plane parameterization. Therefore, instead of two planes, we propose to use two volatile surfaces that are inside and outside the original mesh surface to parameterize rays. So with the two volatile inner and outer surface, now we can parameterize rays coming from any directions, achieving the parameterization of a full 360-degree ray space. Now let's extend this to our animatable avatar task. So in this work, to create the inner and outer surface, we first deform the template mesh. It can be any template mesh. It can be a pre-scanned template mesh, or it can be a SMPL model. The most commonly used human template model. We can use any template model. And then we deform this template mesh into the target pose using the off-the-shelf deformable human model. And after we obtain the deformed mesh here, we dilate and erode the original surface V along its vertex normal directions to create the outer and inner surface. So let's say we have this vertex on our deformed mesh. And for each vertex, we know the vertex normal direction. Then we create another dilated mesh by offsetting the original vertex with some prefixed offset D along its normal direction. And this is how we create the inner shell like this. And then we also create outer shell. We create inner surface and then outer surface. So now that we have our outer inner surface, we can parameterize our array by UV coordinates of its intersecting points with each surface, which are U out and U inner. And again, since we can decide the color of this pixel just with a single forward pass, where we give the two intersection points U out and U inner, we can obtain the color as output. And the rendering speed of this light field representation is very fast because we only go through one single forward pass to get the color of this single pixel. So this is how we achieve a very fast rendering speed. So I will skip through other details, but after doing this, now we can have this real-time performance while achieving the comparable rendering quality with the neural actor on the left, which is extremely slow, but we work at real time, and we also show a comparable rendering quality. And now let's quickly talk about how we can achieve the affordability in 3D human digitization. So here we focus on the reconstruction from sparse views, but this introduced challenges like missing details and occlusions. So to address this, I propose leveraging our 3D human prior and temporal information. And now let's first take a look at how we can use 3D human priors. So here I use 3D Gaussian splatting as it is fast and photorealistic. And 3D Gaussian splatting is a technique that represents a scene as a set of 3D Gaussians. And each Gaussian is represented with a set of parameters that decide its shape and position, and the pixel color. And the pixel color here is computed by blending the Gaussians that intersects with the camera ray coming out from this pixel. And to initialize these Gaussians, a common approach is to first compute a point cloud using structure from motion, which is the process of estimating the 3D structure from hundreds of cameras. And the 3D coordinates of these points are then used to initialize the Gaussian centers. So however, this initialization becomes challenging in our sparse input setting because computing this SFM point clouds requires hundreds of images, and we only have sparse input views, like 3 images from 3 cameras. So this problem is even more pronounced when dealing with humans, which involves self-occlusions and depth ambiguity. So therefore, instead of structure from motion point clouds, I propose to leverage 3D human prior for the initialization of the Gaussians. So specifically, I propose to use the 3D human template. So let's first define what is a human template. So human template is a function that generates post vertices that correspond to the given pose and shape parameters. And it can be obtained from multi-view images as few as like single image or 2 or 3 images. And SMPL model here is one of the most commonly used human template model, and we will also use SMPL in this work as well. So again, the initialization can be done by placing Gaussians on the surface of the SMPL human template model. And this approach ensures a dense and structured initialization. So instead of using SFM point clouds, which can be only obtained where we have like hundreds of images, we are going to use SMPL model that can be obtained only using a single image or two or three images. And then after obtaining the SMPL model, we are going to attach the Gaussians on that model like this. And this is how we enable the robust initialization, although we don't have 100 input images. And next, I will go into more detail on how we determine the positions and other parameters of the Gaussians. So in order to compute the Gaussian parameters, we propose to define and anchor Gaussians on the template surface and regress their parameters in the 2D UV space of the human template to match the input image. Specifically, for every pixel of the UV map, we attach a Gaussian on the corresponding 3D human surface point defined by the 1-to-1 UV mapping. So each pixel on the 2D UV map corresponds to a unique 3D point on the surface of this SMPL model. And we are going to define one Gaussian per every pixel on the UV map like this. And then we are going to give this as input. And also we are going to give our input images so that the network can now regress the Gaussian parameters that matches with the input appearances that we have. And then after we have those Gaussian parameters, we can rasterize them to have our nice 2D images. So I will skip the other details, but I would like to mention the important thing here. So although we can use the human template model to initialize the Gaussians, however, the details that extend beyond the surface of this template model, such as these hairs, or loose clothing like dress or skirts, are difficult to model with the Gaussians attached only onto a single human template surface. This is because the human template represents a naked body model, and they do not have hairs or clothing. And this creates a geometric gap between the template and the real human. So therefore, to narrow this geometric gap, we propose to utilize multiple scaffolds. Specifically, we offset the template mesh along its outward vertex normal direction to create multiple scaffolds. So as I mentioned before, let's say this is the head of the SMPL model, original SMPL model. Then for each vertex location, we offset the vertex along its vertex normal direction to get the offsetted scaffold. And we repeat this. For example, in this work, we used 4 outer scaffolds. So we repeat this for 4 times to get 5 scaffolds in total. And then we encode the information gathered from the entire levels of scaffold into the input, and then we regress the Gaussian parameters that corresponds to each scaffold. So I will visualize how we can do that. So now let's look at how each different scaffold can contribute to the modeling of the displaced details, in this case, the hair. So here, each column corresponds to the different level of scaffold. For example, V0 denotes the innermost scaffold, which is the SMPL surface itself. This is the SMPL surface. And V1 to V4 denotes the outer scaffolds created by dilating the SMPL surface. These are our scaffolds. And the rightmost column shows the combined result. So let's see. Every time we add the outer shell, we can reconstruct better details. So we can see that each different scaffold effectively contributes to the modeling of the hair volume. And here we show the final results, final comparison results. Our results are at the rightmost column. And we can see that compared to other single surface-based methods, we can generate and reconstruct better details. So one key insight from our work is that incorporating a 3D human prior can help with sparse view reconstruction. And now I will talk about my most recent work. So for a truly affordable human digitization, the ultimate accessible setup would be captured with just some single mobile phone, something anyone can do. And this naturally leads us to a more challenging problem of monocular input reconstruction, where we aim to reconstruct a 3D human from just a single view. So with monocular input, the main challenge is missing information. So we only see part of the subject, making unseen regions ambiguous. For example, given a side view image, rendering the frontal view is difficult since there is no direct information about the face or frontal body. So how we can reconstruct these unseen parts while maintaining high fidelity? That is what my next approach addresses. So let's first take a look at this example. Let's say that we have a video of a subject moving in front of the camera. At the current frame here, we only see the side view, so reconstructing the frontal view seems difficult because we don't have any observation about the frontal face of the subject. However, if we look at the previous frames, we can observe frontal, side, and back views of the subject. So assuming that the subject is constantly moving in front of the camera, we propose to gather information from previous frames to be able to accurately reconstruct missing details in the current frame. So I will skip through the details, but we use the 4D correspondence provided by the human template model so that we can gather, for example, here, we can gather the back view of the head of the subject, and also we can track the face and the side face. And then we gather those informations to the canonical space every time we have new observation. So here, let's see some results. So although we cannot see the details of the inner garments in the current view, we can sincerely generate and reconstruct the inner garment because we have already observed the details in the previous frames and we have stored that information in the canonical space. So here we are proposing to actively use the previous information that is stored in the canonical space. And the important takeaway here is that leveraging temporal information compensates for insufficient observation in monocular view reconstruction, enabling accurate and consistent results aligned with past observation. And now let's talk about our last task, which is enabling the easy to interact avatar construction. So imagine taking just a selfie and from that, not only rendering the web views, but also animating yourself effortlessly by just providing a video. And this level of easy interaction is what we want. Oh, I can see someone has a question. Please go ahead.
Yeah, just really quick. I think the Zoom meeting ends soon because there's a 40-minute limit.
Oh,
I'm
sorry about that.
no
Okay.
worries. I can create a new link and I can put it in the chat if that's okay. So sorry to interrupt.
Oh, no, no worries. Or we can maybe quickly finish. What do you prefer?
Um, we have 4 minutes left.
For
So
me, okay.
yeah.
Yeah, we can have another link then.
Okay, sounds good. So sorry
Yeah,
to interrupt.
no worries, no worries. Can you see my screen slide?
Yes, we can.
Yeah, okay. I will quickly go through how we can enable this animatable representation very quickly. Um, so to animate an avatar, we need a driving signal to control pose or viewpoint changes. So here, the driving signal is this SNPL model here. So the common approach is using the 2D skeletons or SNPL normal maps from the driving video, like what we can already see in the video. And while these provide structure guidance, they lack appearance details and are too sparse, leading to inconsistencies. As you can see in this example, you can see those flickering artifacts. And to address this, we propose a denser appearance-aware driving signal. And what I mean by that is instead of relying on sparse signal, we first generate an intermediate rendering results using an off-the-shelf human rendering model, such as the one based on the 3D Gaussians that I introduced just before. And we then use this feature to drive a diffusion model, providing a dense signal that not only retains structure information, but also retains appearance details missing in 2D skeletons or normal maps. So here we use uh, dense driving signals. And also, beyond choosing the right driving signal, another key challenge is generalizing to real-world data, because ultimately we want our system to work on ourselves and real-world images. So most human digitization methods are trained on studio-captured multi-view datasets, which lack the diversity of the real world, such as lighting, skin tones, and clothing. Also, capturing studio data is expensive, limiting its availability. To address this, we propose to incorporate in the wild internet videos, such as videos from YouTube or TikTok, which provide abundant and diverse real-world data. Um, so let's see the animation results. So just from single image, we can naturally animate the avatar. And let me show some features on selfies. So here is a photo of myself. And with our approach, I can not only generate nowhere views of myself, but also make my avatar move naturally. And in this case, I can make myself dancing like a professional dancer on the right, although in the real life, I cannot really dance. And here is another example, this time using an image of my postdoc advisor back in CMU, Fernando. We can animate him just using a single selfie of him. And here is another features on the celebrity images. In today's talk, I introduced how I enabled the democratization of the 3D human digitization by making it efficient, affordable, and easy to interact. And this is the end of the talk. Thank you for listening to my talk.
Thank you. We can do a Q&A if that's okay.
Yeah, of course. Oh, go ahead, Jessica.
Oh no, I was just saying thank you so much for coming and giving us a talk and hearing about your research.
Oh, thank you so much for the kind words.
But yeah, if anyone has questions, feel free to put it in the chat or just unmute. I think both options should be okay.
Oh, yeah, and if you have like further questions, please feel free to email me. Yeah.
Mhm.
Um, mm,
I have one question about how some of these state-of-the-art
mhm,
models can be used in VR or something like that, given
mhm.
latency and also like quality of the avatars.
That's a very good question. Uh, for the actual use in VR, those examples that I introduced today, except for the one that is using the light fields, other works are pretty slow, I would say. So you have to pre-generate, for example, if you want to have this Nobel view video, then you have to pre-generate the Nobel views in advance before you using the VR headset to looking at them. But mm, for the live field work, definitely it is a real time where you can generate the Nobel views in real time, and also the ones with 3D Gaussians, they are mostly very fast because they use fast rasterization techniques. So I would say the fastest rendering technique that is out there is 3D Gaussian rasterization technique. So if you want to use those kind of human digitization works with your VR headset, I would recommend to use this 3D Gaussian based works.
Okay, and then what about the latency?
Mhm. Latencies like um
Like for any real-time generation of gestures
mhm.
or just how the visual representation of an avatar? So I guess how real-time would it be?
It really depends on which kind of work. So for example, like let's say you are targeting for you want to just view reconstruct a static human and view it from any angles. So that can be considered as a static Gaussian reconstruction problem. And in that case, it can achieve like hundreds of like sorry, like frames per second. But let's say you want to watch 4D reconstructed Gaussians, then since you should reconstruct 3D Gaussians that are smoothly transitioning from previous frames, that means you have more complexities, and the sodas I would say they hardly achieve 100 frames per second, but it is still real time, I would say.
Okay, so I guess what I'm
Mhm.
hearing is it's easier for the 3D environment in VR because you're
Mhm.
pre-generating than it is like an avatar, right? That is,
Yes, yes.
okay, that makes sense.
Mhm.
Do we have more questions? Okay, I have another question. Um,
Okay.
bit of a tangent, but I work in both VR and computer graphics research.
Mhm.
And something I've noticed is that when I do human factors or HCI feel like
Mhm.
there is a need to address some of the misuses of computer graphics research sometimes,
Mm.
especially with avatars, because that's also what I work on. I
Mhm.
feel like sometimes I'm working for a company right now, and
Okay.
sometimes I'm like, what if someone's using this for bad or something like that?
Uh,
I'm just curious about your opinions.
that's a very good question. And yeah, I have been also thinking about that, but
Hmm.
mm, mm, right, right now, uh,
Hmm. No worries. I was just curious because it's something I think of because I also do like human factors sometimes. So I'm
mhm.
kind of like, what are the implications of my work in computer graphics or something like that?
Yeah, I do believe like those kind of animated representation can be seriously misused. I'm
Hmm.
also concerned about that, but hmm, just only thing I can do is just hope that the users don't
Mhm.
do not use it in like with bad intentions. The
Mhm.
only thing that I can do is just hope that and just for example, um yeah, I would say I for now I'm not aware of some practical solutions for that. Just I'm hoping for everyone that is using my work to not to use that in like bad applications. That's what I'm hoping for.
Mhm. That makes sense. Yeah. Do you have more questions? I'm not sure if you do, but I have just the last section of this talk is if
Mhm.
you have any related papers besides the one you presented,
Mhm.
if you want to just put a link or something for people to read if they're interested in this area,
Mhm.
that's kind of the last section, and after that, we can just conclude it.
Oh, or maybe I can send the list of interesting papers to your email and you can share that with other people.
Yeah, I think that sounds good.
Yeah, okay, I will do that then.
Okay, yeah, I think in that case, that is it. We don't have more questions, it looks like.
Mhm.
But if someone has follow-up questions, can they email you or what do you prefer?
Yeah, or just feel free to email me.
Okay, yeah. Okay, great. I think that
Mhm.
should conclude the event. Thank you so much
Mhm.
for joining. I'll put this on YouTube and I'll share the link with you as well.
Okay, thank you so much for your time, everyone. Have a good night.
Thank you.
Thank you.
Thank
Okay,
you.
bye.